Okay, let me demonstrate a screen. Today I am a speaker, and my talk is named as Properties of Stationary Random Node. It is a continuation of the previous talk on this seminar in previous semester, where I constructed a special type of random node. It was obtained as an image of smooth curve under the random matrix, which was a random field, Gaussian random field, with good covariance and zero mean. And the main feature which was proved in last talk was that this node can have arbitrarily complicated structure with positive probability. So now let us continue to study of this object. And today I want to propose you the construction of stationary random node. So it will be a family of random curves, which is stationary, and discuss its properties, both probabilistic and geometric. Let us begin with the construction. For myself, I name this construction like Ornstein-Uhlenbeck equation with interaction. Let's see. So I am supposing that A is a generator of a unitary semigroup in R3. So if A is a matrix such that the following matrix value equation, if we start from the identity matrix I capital, has a solution which is a semigroup of orthogonal matrix. Suppose also that WT is a standard linear process in R3, so it has zero mean and identity covariance. And consider a following equation with interaction. Here we have a linear equation with the additive noise WT, and we consider the following equation. XUT is dxut is equal A multiply XUT minus MT dt plus dWT. Here is usual XU0 is equal to U, and we consider together all trajectories which start from all points of our space R3. Mu T is an image of the initial measure mu0 under this mapping X, and MT is the center of mass of the system. So it can be obtained via both these formulas, or this is integral with respect to R3 of U, or against mu t, or this is the integral against mu0, but from the XUT. I suppose that the initial measure mu0 belongs to the space M1, where M1 is the set of all probability measures with the finite first moment. Then this equation can be solved explicitly as follows. Let us consider, let us integrate it with respect to mu t again. Then we get that dmt is equal dwt because the first summand with dt will disappear. So one can get the following, that mt is just m0 plus wt, And then it is trivial that the equation for difference x ut minus mt became to be deterministic. Since then, x ut minus mt is equal ut multiply u minus n0. So one can say that we have the following solution. The center of mass is floating in R3 like Brownian particle, and all measure of mass distribution is whirling around this center of mass. You can see this illustrated picture, how it looks like. We have a blue trajectory of the center of the mass, and these vectors from the center of the mass to the points u1, u2, u3 are rotating in the space. Now suppose that a visitation that mu0 is a visitation measure of smooth closed curve gamma 0 in R3, which is parameterized by the function phi f0 from the space of periodic twice-the differential function 0, 1. When I mean twice periodic, I mean that this function are continuous, and together it is derivative periodic on the this interval. Yeah? So define mu0 as a visitation measure. So mu0 from the set delta is an integral of the indicator of delta from f0 as ds. Then mu t will be a visitation measure of the new curve gamma t, which is trivially x from gamma 0 t, and parameterized by fts, which is x from f0 as t as belongs to 0. As it was mentioned before, the curve gamma is rotated around its center of mass, which moves like Brownian motion. So one can consider this picture. Here is our curve, which is red, and it is rotating around the center of the mass. And of course, if we start from the curve of special topological type, for example, it can be unknotted or knotted closed curve, then during this motion, the curve does not change its topological type because, as we mentioned, one curve here obtained from another just by a fine transformation of special kind. It's shifted on the some increments of Wiener process W and rotated by the some orthogonal matrix, which does not change shape of the curve. But with the help of this gamma t, new random curves will be constructed. How will we construct it? Let us consider R3 valued stationary random field defined in R3 as follows. Its coordinates psi1, psi2, psi3 are independent centered Gaussian random fields with covariance like this. From time to time, I will use not u minus v square, but one half of u minus v square. But it does not make any influence on the result. Only convenient, only calculation became much more convenient. And introduce new random curve, gamma t, which is psi of gamma small t. So we have this floating random curve like this one. Then we maps this floating random curve by Xi from R3 again into R3, but new random curve has new properties. So it looks like following. Gamma t is a smooth closed curve without self-intersection. We discussed this previous time that it cannot have a self-intersection with probability 1. And gamma t has arbitrary topological type with a positive probability. With positive probability. It was written in my preliminary paper, which is posted into arXiv. Now let's check that gamma t is a stationary random node. Namely, if we consider such random process in the space of a function, then it is a stationary random process. Let us see idea of proof. The curve gamma t is moved by the mapping xut is equal ut u minus m0 plus wt, where m0 is the center of mass of gamma 0. Hence, mt, as we said before, the center of mass of gamma small t at time t is just m0 plus our winner. Now discuss the subsequent values of x, u, t, k for different moments of the time, t1 and tn. Then the increment can xutk minus xutj can be written as follows. It is equal to the following. This is simple calculation, but I insist that it is rather interesting. You see, firstly we do simple algebra, but finally we get the following answer, that this difference utk minus xutj is equal to xutk plus s minus xutj plus s. Then it looks like us, which is applied to the difference, which is very similar to the difference for xutk minus xutj, despite we have here us outside of brackets and us minus 1 applied to the increments of Brownian motion. But see what happened. If we fix f, this is a parameter of the shift when we study stationarity, then us is a fixed unitary or orthogonal matrix. It does not change length and angles, and also it means that these increments us minus 1, wtk plus s minus wtj plus s becomes to be again increments of new Wiener process, standard Wiener process. Yeah? So one can say that that using the covariance function of psi, and then usual conditioning firstly on w, then taking full expectation, we get that we have a really stationary random process. Next one. It occurs that this random process has mixing property. It is important because what a picture we are considering. We are considering a randomly moving node which change its topological type. But we want always make some measurements, and I'm supposing we will consider this random knot as some model of for long polymers in biology. Then we need to do some measurements, and of course we will take average, and we have to know that this average tends to some limit. In order to do this, to know this, we need some mixing property of our stationary process. Since our process is obtained by the substitution of some randomly moving object governed by a Wiener process into the random field which is independent from this Wiener process, then of course we will prove our mixing property using some Gaussian structure of the our field psi. So I'm claiming that for area square integral functionals f and j from gamma t, we have the following. Here, t with small index t is a shift of the functional from our stationary process. So we have to process. Again, I will give you idea of the proof. And let us start from two standard jointly Gaussian random waves which are correlated with alpha. Then it can be proved that the expectation of the product of two Hermite polynomials from eta 1 and eta 2 is equal to such very nice formula. This is k factorial Kronecker tilde km, and coefficient of covariance that's alpha k in k power. And the explanation is simple because using stochastic exponent, one can easily check that the conditional expectation of the Hermite polynomial from eta 2 with respect to eta 1 is equal alpha m, the same Hermite polynomial from eta 1. Then now let's start studying the process. I will consider just very simple case. One coordinate depends on the Wiener process t in order to simplify calculations. One can check that if we have f of zeta t1, then it can be expanded into the series of Hermite polynomials of such kind. Then j from theta also can be expanded into series of Hermite polynomials of such kind. And then it is easy to check. It is easy to check that this expectation, first we conditioning it with respect to W capital and get the following. And we will calculate this precisely, but this exponent, but it's now easy to see that the series converge to A0, B0, which is exactly equal to product of the expectation. Due to this, we have mixing property, and gamma t is ergodic process. Since then, one can say that if we have some functional from gamma, then the average of our data, which we get just investigating gamma, will go to the expectation of this function of gamma 0. Now let's consider some geometrical characteristics of gamma. The first one is length. I suppose that initial gamma 0 has natural parameterization. So for any t, we have the tangent vector f prime t has norm equal to 1. And from now, I suppose that the covariance of our vector field psi is equal not exponent minus difference of the u minus v square, but with 1/2. It change only simplicity of calculations, but in very convenient manner. Then we have the following properties for xi prime. Xi prime is a matrix because xi is a vector valued mapping, and due to this covariance, it is independent from xi and consists of IID standard random variables. This is convenience of 1/2 in the exponent. Then for arbitrary orthogonal matrix V, we have that xi prime u multiplied on V is has the same distribution as xi prime u. Consequently, one can say that for any A from R3, this expectation of xi prime u A norm is equal to the norm of A multiplied on expectation of norm of eta, where eta is just standard Gaussian random vector in R3. Why it's happened? Because we always can rotate. Firstly, we can divide A by its norm and take this norm away from the expectation. And then we can rotate A into the vector with coordinates 1, 0, 0. Then we have the first row of the xi prime, and it is exactly standard Gaussian random vector, so we can calculate this expectation precisely. And since then, the average range of our random curve gamma t is equal to this expression 2 multiplied by square root of 2 divided by pi. And it is interesting to see that despite we have xi as a stationary random field, the average range of gamma t is bigger than range of gamma small t. It is now 1. We consider it natural parameterization. So despite that we have rotational invariant and stationary random field, so its characteristics doesn't depend on rotation, moving along the space. It expands the curves. Yeah. Now let us consider another one characteristic, because of course it is interesting to watch and not only watch but investigate the topological properties of gamma t. Topological properties of gamma t, and what can be investigated. It is known from the knot theory that every knot has a special can be represented as follows. We have a plane and some points on this plane, and knot is organized from the bridges between those planes under the plane and above the plane. The idea of obtaining invariant of knot from this representation is the following. One can ask that any bridge will be unknotted. So situation which is drawn in my picture is not permitted. You see, one bridge is noted, but in a case when we want to have the topological invariant of the node, we have to consider only representation when each bridge is simple unnoted curve. Then the minimal number of such bridges in such representation is the invariant of it. But unfortunately, I cannot calculate such invariant, but still it is interesting, I think, to calculate the following number. We just have an arbitrary plane. It cuts our node, and we are looking for a number of bridges which is placed above our plane, despite that some of them can be noted. Still, it reflects some complexity of them. Since, as we mentioned, that for orthogonal matrix V, the random field V multiplied xi is equidistributed with the xi, with initial xi, then it is enough to consider only planes where the first coordinate is equal to fixed number a0 and other coordinates are fixed to 0, are arbitrary. Then a number of bridges coincide with the number of upcrossings of the level A by the process xi1 from F0S. F0 is the parameterization of our node, our curve gamma 0, small gamma 0. You can see why it is so. Since then, we have a good formula for number of upcrossings. This is a well-known Rice formula, which we use for stationary process now. Oh, by the way, okay, here still is not stationary, but further I will use it. So QS is a joint density of xi F0S and its derivative with respect to S. And because we still have natural parameterization, and xi1 is stationary random field with no characteristic, with no covariance. We now have that xi1 and this DDS xi1 F0S are non-correlated. So they are Gaussian, they are independent now. And due to this, we have such properties, and they are standard. And due to this, one can achieve that the expectation of the number of upcrossings is 1 over 2 pi e minus a squared over 2. By the way, the multiplier e minus a squared over 2 was expectable because it is also a general property of Gaussian stationary random fields of processes there. The expectation of the number of upcrossings in our one-dimensional case, or more generally Euler characteristic of the levels, it has the same logarithmic asymptotic as the maximum of the process. Now process is stationary, maximum of the process has the same characteristic as one of its values. So only we change here the multiplier 1 over 2 pi. Okay, let's go further. In order to understand, is it possible to have a Gaussian limit for normalized integrals? You see here, we usually, after we have a law of large numbers, we need to check if we have the asymptotic normality. We have to study the speed of the mixing. And now it's very easy to do. You remember that we estimated the expectation of products of two functionals, and you remember that there we have the 1 over 2 now, norm of the increment of inner process. I put here WT instead of increment, and in dimension 3 and bigger, we had that it is equal to t plus 1 in minus 3 over 2. So we can say that we can see that this integral is converged, and moreover, one can check that, for example, this number of approaching has finite moments. It can be found in the book of Robert Adler and Jonathan Taylor, Random Fields and Geometry, Theorem 1151. So we have that for arbitrary t which is greater than 0, the number of approaches has a finite piece moment. It means that now we are in a position to check to apply the central limit theorem for weakly dependent random variables, like it was done in the book of Ibrahimov and Linnik, dependent stationary sequence of random variables. But after this, we understand that when we measure the parameters of this random node, then we have in average we can calculate it. We expect that in average we get fixed number now, and now it's time to ask what this parameter says us. And what is happening here, that if we consider, if we look for this number of approaches expectation, this expectation is less than 0. Yeah? Even for h equal to 0, which we expect must be most most interesting case, because this value looks like biggest. It is less than 1. It means that with a big probability our gamma t is almost flat. So now let us look for some functional which can characterize for us the complexity of this node. Such functional exist, and this is energy of gamma t, and it looks like the following. This is the integral from double integral with respect to all parameters S1 and S2. Here is one of the norm eta S1 minus eta S2 square minus 1 over gamma eta S1 eta S2 square. Multiply on the norms of the tangents because we need the integration with respect to lattice of our curve. Here, eta s, this is xi from f0 of s, our parameterization, and gamma eta s1, eta s2 is a distance between the points eta s1, eta s2 along the curve gamma 0. So let me show you a picture. If this is curve gamma 0, then green line, this is smallest part of the curve which connects the point eta s1 and eta s2, and the red line is just the segment which connects the same points. So the length of the green line is exactly gamma eta s1, eta s2. From this picture, it is clear that the energy is always non-negative, yeah, and is equal 0 only for the segment of the line in the space. And this energy was, I think, it was introduced, as also said, by Möbius, but I think that it was intensively studied firstly in this paper by Mike Friedman, Zheng-Xu He, Zheng Van Wong, Möbius energy of knots and knots, annals of mathematics in 1994. Here there are some properties that E energy doesn't depend on the parameterization. Of course, it is so, because we can see in this integral, we can see the derivatives in the last line, and then also it does not change under affine transformations, but of special time. This is not multiplication on the matrix of U vector U, but only on the number alpha. And it does not change the energy. It is interesting that it does not change on the inversion with respect to a circle, which is called Möbius transformations. And also it is interesting that minimal value of E is achieved on the circle and equals 4. And what I have to say that if we consider again this integral, it can be we have to explain why it is fine. Yeah? And the reason is following. If we have, as we consider on the smooth curve, if we have smooth curve, then near every point, it looks like a part of the circle. So, roughly speaking, in the first denominator, we have something like 2 sine s1 minus s2 divided by 2 in square, and in the second denominator, we have s1 minus n2 in square. And then if we do usual calculations, we will see that in the denominator, we will have at least third power, which, excuse me, at least, yes, it is at square, at least fourth power, which cancel this denominator. So it looks that it is finite for smooth curve. It is true. Then why this energy is interesting? Because it is related to the crossing number. What is this? Suppose that we have our knot gamma 0 in the space, and suppose that we have some plane which has normal vector theta of unit length. Then we can project our node onto the plane, and it occurs that this projection can have some crossings. For example, in the picture which I propose to you, we have node gamma 0, and after projection, we obtain 4 crossings. So for this fixed theta, number of crossings in its projection, n small theta gamma 0 is equal to 4. Now, the average crossing number is the following. This is 1 over 4 pi. So this is average with respect to theta. We just integrate this n theta gamma 0 with respect to the uniform distribution of the unit sphere in R3. Then this is average crossing number. And it occurs that this average crossing number can be obtained in very different ways, but we already have seen this formula. We discussed House formula when we discuss number of linking number of two curves, and here this Gauss formula present linking number the curves with itself, and you see here the following. In the nominator, we have such product of 3 vectors, tangent vectors in the point S1, S2, and a difference, the vector which connects point eta S1 and eta S2. And this is nothing else than when we take absolute value, this is just a volume of the parallelogram which is obtained from these 3 vectors. And in the denominator we have the difference between eta S1 and eta S2 in power 3. By the way, this integral is finite, of course, due to the circumstance that we have one difference already in the denominator, and when S2 approaches S1, then eta prime S2 tangent vector approaches eta S2 with all at least all capital S1 minus S2 square, so we get desired order of difference S1 minus S2. Then one can try to define the topological invariant, and this topological invariant is the following. It is minimal crossing. It is a minimum of such crossing numbers which we discussed, but here I consider not only gamma 0 itself, but all gamma, curve which represent nodes isotopic to gamma 0. So overall, all isotopic nodes. Then this star of gamma 0 is a topological invariant. Evidently, it is smaller than average crossing number, but now let's see this Gauss formula for crossing number, and let's formally just cancel one. Just cancel one difference, eta S1 minus eta S2. We get this square here, but we have here some still like scalar product or no, a vector product of eta prime S1, eta prime S2. Then it goes to 0. And you remember that in the energy definition, we have 1 over eta S1 minus eta S2, of course, minus something, but the formula for energy can be rewritten where we leave only this eta S1, S2 minus eta S1, and some normalization curve. So from this, it looks like n gamma 0 must be less than energy, and it occurs true. So there is an estimation which also can be found in those article of Mike Friedman with forces, which I mentioned, of the such case that if we have the gamma energy eta or E capital from gamma 0, then the minimal number of crossings is connected to it with such inequality. But if we have minimal number of crossings, then we can imagine variety of topological types of nodes. And using this idea, the following theorem also was proved in this article, that the number of different types of nodes with energy which is less than some threshold is not greater than such a value. By the way, this is not a very big value, 24 in 1 over 2 pi. This is like 1 and something. So it's even less than 2 in m power. So from estimation of energy, we can get the estimation of complexity of the node. And now see what happened. If the parameterization is natural, then one can find the following estimation for energy. This constant C does not depend on any special curve, but here we have and delta is any positive number. Of course, C will depend on delta. But if we fix positive delta, we have the following estimation. Here is F2 prime, but this is natural parameterization. And this is a problem right now for me, because when calculating this parameter, this value for our case with random field psi, we will get norm of psi prime from some point. Of course, this is a norm of standard Gaussian matrix or applied to some vector of unit norm, but we will get this norm in a very big power, because this is a second derivative. When calculated it, we already will have something like 2 first derivatives in denominator. Then we have this moment. So we'll get singularity. From this point of view, now I'm studying the distribution of the energy for our node and hoping to find the estimation for complexity of obtained node. Maybe that's all what I wanted to say today, and thank you for attention. If somebody have questions or comments, I will be happy to answer you.
So you have some estimates from above for number of nodes when you study this energy.
Yes. I hope that first of all, this estimation is true. So what I need in my case, this M is the energy of my node. So I can say that I have a random value this epsilon from gamma 0. It's random, but still I know that this random node has a complexity between such number of nodes. Of course, it is a great number, but still it can be at least can be calculated.
And lower bounds for number of nodes.
You see, I think that we can proceed exactly. We can repeat. I think that there are no that it will be exactly the same. Why I am thinking so? Because if you remember the proof from my previous talk, what was done? That we have to control exactly second derivative and approximate by this derivative the arbitrary periodic function. Yes. Then you see when we control the energy, we control the integral from the second derivative. And if we and then I think that we can approximate again the arbitrary function with such value of integral that is greater than our that has, for example, fixed value. So I think that we can get arbitrary node which is allowed in this inequality. But I have no proof. I just think that it is true because when you begin to think how complicated can be this node, then you immediately get this estimations of the second derivative of curvature of the node. Even it goes to Milnor, that Milnor proposed as a number characteristic of the node is total curvature. Just total curvature. Again, it occurs that minima of Milnor energy is again achieved on the surface, arbitrary. But it has no such a good property. If we get any epsilon, which is greater than 0, take the Milnor energy of the surface plus epsilon, then there are infinite number of nodes which has the energy which is less than this plus epsilon. So from this point of view, it looks like we have to control the second derivative, and if we just have a threshold for some integral, then we can get everything with this integral which is lower than this threshold. But this is just idea. I did not do this.
Thank you.
Okay. Okay, if there are no other questions, I think that we have next talk in the middle of May. Georgi, am I right?
Yes, it is in 2 weeks.
Mm-hmm. Okay, so please be please pay attention to announcement, and who will be the next speaker?
It will be Katya Glинina.
Mm-hmm. Okay, okay, then see you. Bye.